Good evening. Welcome everyone to tonight's Royal Meteorological Society Yorkshire Centre's talk. My name is Kamalika Sengupta. I'm the chairperson of the Yorkshire Centre, and it's my pleasure to present to you the talk tonight. Those of you who are joining us for the first time, please note that this talk is being recorded and it will be made available on YouTube later on. Throughout the talk, you will have the chance to ask questions to the speaker. Please use the chat box at the right-hand side of your screen. If you click on the arrow pointing to a bar, the chat box will open and you can type in your questions anytime you have it. To enlarge your screen, please use the arrows facing away from each other at the top right corner of your screen. Tonight's talk is going to last for about 30 minutes, after which we will have about 10 minutes of question and answer with the speaker. I'll now introduce the speaker of tonight, who is Neil Donahue. Born in Pittsburgh, where Neil is joining us from tonight, Neil did his undergraduate in physics from Brown University. He then did his doctorate from MIT, working with Professor Ron Prin on non-methane hydrocarbon chemistry of the marine environment. Neil then did his postdoctoral research at Harvard University with Jim Anderson on gas phase chemical kinetics. Neil joined Carnegie Mellon University in 2000, and currently he's working there as the Lord University Professor of Chemistry within the departments of Chemistry, Chemical Engineering, and Engineering and Public Policy. Neil is also the director of Steinbrenner Institute for Environmental Education and Research, as well as fellow American Geophysical Union, American Association for Aerosol Research.
Brilliant. Well, thank you very much, Kamalika, and also to everybody online who's joined. I see that there's a pretty tremendous geographical diversity in the sign-ins on the chat, so that's one of the little side benefits of a virtual world these days. So I'd like to talk to you a little bit tonight about some work we're doing. From Kamalika's introduction, you noticed I had an undergraduate degree in physics, and I thought as an undergraduate that I might spend time doing things like elementary particle physics at CERN, and now I am. I'm doing particle physics at CERN, but it's a little different from the sort of elementary particle physics that you may know about, and actually it's in that project where I first met Kamalika while she was an International Training Network doctoral student working with Ken Carslaw at the University of Leeds as part of this consortium that we'll be talking about tonight. I am looking at the chat, so if something is confusing, I may have the opportunity to clear it up quickly if you express confusion. Otherwise, I will certainly leave time for some talks at the end, some questions at the end, excuse me. So first, I would be remiss if I didn't advertise our new journal. For those of you who are academics, the Royal Society of Chemistry now has a new journal in its environmental portfolio. It's the fourth in this little family of journals, and it's set to be an open access journal called Environmental Science Atmospheres. And I have the honor of being the first editor-in-chief of the journal. We're rolling out our first issue in a couple of weeks. There are already papers online, and I strongly encourage you, if you are an academic in this area, to consider our journal for your submission of your excellent work. We hope to really launch this and make it a leading journal in the field. And for the next year and change, it's both open access and there are no fees for having the publication. So it's also an attractive place to start and launch. So the end of the advertisement and on to the science of the day. There are two main things about fine particles in the atmosphere that drive us to study them beyond the fact that they're quite interesting and sort of endless fascination of chemistry and physics. And the first is that they kill a lot of people around the world every year, 5 to 7 million people. around the planet every year. It's something like 15% of all mortality. And so they're a very big deal as a menace to public health. And therefore, mitigating, reducing the levels of fine particles is a crucial public health issue. And this is a kind of a classic photograph of Beijing looking at the Forbidden City. On a very hazy day on the left and on a so-called blue sky day on the right, though the fact that there are mountains in the background isn't even visible on this blue sky day. And so Beijing is quite famously polluted, and actually the pollution levels have gone down pretty dramatically over the past several years. Now, the second reason we care about fine particles in the atmosphere is they're central to climate. And in fact, most of the uncertainties about climate. We understand the climate system extremely well. There are, however, a few elements of climate that remain difficult to pin down exactly, and particles and cloud droplets are really at the center of all of the uncertainties about the atmospheric effects of climate change and the atmospheric causes of climate change. The way clouds respond to changes in the climate system is one of the major elements, but also the way that fine particles that serve as seeds for clouds have changed over the past 250 years represents one of the largest uncertainties in what we call climate forcing. And that's illustrated quite dramatically by this image from space taken from the International Space Station or the Space Shuttle. I actually cannot remember. And this image spans more than 1,000 kilometers on the side. That's the western coast of the United States that you see on the edge there of the image. And this is the sort of marine stratus deck that you find on the eastern ends of pretty much all of the major ocean basins. And these stripes, these sort of scratches along are ship tracks. And they're not smoke directly coming out of the ships. This is the sulfur dioxide that's emitted as part of the bunker fuel that many ocean-going vessels burn or used to. It's being banned while they're out at sea. And the sulfur dioxide is oxidized to sulfuric acid that increases the number of particles in the atmosphere. And I'll show you some data on that in a second. And that those sulfuric acid particles, it increases the number of particles that are present to seed the liquid droplets in these open cell stratus clouds, and it actually changes the cellular structure of the cloud so they fill in and they whiten. And so that white stripe is a complete change in the microphysics of the clouds. It's the most dramatic implication. Of course, the ocean is effectively black, the wine dark sea, and so building the contrast of putting white clouds above the dark ocean dramatically changes the reflectivity, the albedo of the planet, and that changes the amount of solar energy that the Earth absorbs, and therefore changes the amount of forcing from the sun that the climate system receives. And so how that has changed since the Industrial Revolution is a major uncertainty in climate. So let's start this story. About a dozen years ago, we were going to Moran's Oyster Shack in Galway, and my daughter found this sign on the jetty here, and she was pleased with herself because it was a little bit edgy. But the idea is that we really are on a precipice in terms of climate, and at risk for permanent and significant changes to the climate system. And then the aerosol health effects are also a major issue for public health. And this was a dozen years ago. We went back a couple of years back when Keelan finished a term at Trinity College, found the sign again. It had been cleaned off, so maybe we've made some progress over that time. But there is real urgency to this. And as a way of just pointing out, because if you may be aware that the goals or the targets for temperature change, the maximum levels that are being considered tolerable to avoid the worst effects of climate change are a couple of degrees global temperature increase, or a degree and a half is the aspirational goal in the Paris Agreement. And it doesn't seem like very much, but a couple of degrees is a very big deal. The temperature change between right now or 1750 and the peak of the last ice age is about 5 degrees Celsius colder. But you imagine the difference between present day climate and the peak of an ice age. That 5 degree temperature change is is an enormous effect on global the way that the planet looks and its habitability. And so 2.5 degrees is half of that in the other direction. That's a big deal. So that change, even right now, it's a degree warmer than it was in the pre-industrial. And that's really actually a very significant change in temperature from a global perspective. For example, one of the things that's quite likely, even with a degree change, eventually it's pretty likely that Greenland will melt, that the ice sheets over Greenland are going to dissipate over time. Seems more likely than not at this point. Certainly if we get to a couple of degrees temperature change, there's no historical record over the past several million years of permanent ice on Greenland at that kind of elevated temperature. And so that's likely to happen, and it's really a question of when. And so I went to the peer-reviewed literature and found some representation of this. Let's kind of look in, focus in on what's being shown here. So one of the things that happens when Greenland melts, and again, when that happens, we're likely to see roughly 7 meters, 6 to 7 meters of sea level rise as that water melts and flows into the ocean. So this is the current shoreline in southeastern England, and I put Flanders and Holland on here as well. And then if you go to the flood.firetree.net, you can play with this yourself if you're interested and put in a different level of sea level. So if we increase the sea level by 6 meters, this is what happens. So the fens fill in. The Thames estuary experiences a lot of flooding, and big chunks of Flanders and Holland are underwater. So again, let's go this way. That's 6 meters of sea level rise. So that's a very big deal. And the question really is when, not if, that's going to happen. Current models suggest that's sort of millennial, something like 1,000 years or more for that amount of ice melting to happen. But there are elements of that we don't understand fully, and a concern that might happen faster, and there are parts of Antarctica that are likely to melt as well. Sea level rise is a very big deal, and the question of the rate of that is significant. Again, we care about these levels of temperature change. So now let's turn a little bit back to the health effects. Now, I'm going to have a bit of a US-centric view here. First of all, a lot of the early epidemiology was done in the United States, and I'm also based in the United States, so it's the perspective I think of the most. I asserted that there's about 7 million deaths around the year, more than 5 million deaths around the year from air pollution. Let's look at some of the evidence of that. And this is what's called a meta-analysis that my colleague C. Arden Pope carried out by going to the literature and looking at. There now have been many epidemiological studies of the effects of the relationship really between elevated air pollution levels and various health outcomes, but many of which have to do with increased mortality. So in this case, we're looking at the mass concentration of fine particulate matter in the atmosphere, measured in micrograms. That's 1/1,000,000th of a gram per cubic meter of air. For what it's worth, a cubic meter of air weighs about a kilogram. And so that's 1 part in a billion by mass. So these are very tiny mass concentrations of fine particles, but they have a big outsized effect. And then on the y-axis here, we just have the life expectancy. Now, this is in the United States in about 1980. And what Arden did is he looked at 50 different municipal areas across the United States. And there's a clear relationship between life expectancy and the level of air pollution, ranging from about 10 to about 30 micrograms per cubic meter back in 1980. And then going forward in time, 20 years to the year 2000, the Clean Air Act in the United States had been in place effectively since 1970, but with a series of amendments that have put greater and greater restrictions on various pollution emissions. And more recently, there is a standard, what we call a National Ambient Air Quality Standard, on the levels of PM 2.5. PM 2.5, by the way, is the concentration of particles that are smaller than 2.5 micrometers in diameter. So they're very small range of particles that are about 50 times my hair is maybe 40, 30 micrometers in diameter, and so these are 10 times or more smaller than the diameter of your hair. So over that 20-year period, the air pollution mitigation actions have been taken. So you see that the 50 municipal areas now go between about 5 and about the maximum about 20 micrograms per cubic meter. This association line on the left I've reproduced on the right here is a dashed line. And now there's still a relationship between the levels of air pollution and life expectancy. It's about the same relationship. People are living a couple of years longer, and a large amount of that increase in life expectancy is attributable to this improvement in the air quality. More than 20% of the improvement in life expectancy over that time span. So that's an enormously big deal. Now, there's a lot of evidence that this is correlation is not causality, right? So simple epidemiology and showing that yes, there's an association between an observable and an outcome doesn't prove that the pollution, the particles are causing the mortality. But at this point, we have a great deal of evidence that they actually are. And we also have a great deal of evidence that, so even though right now in the United States, the standard is 12 micrograms per cubic meter, that the association carries on to very low concentrations, that there's no obvious intercept. There's no sort of, the dose makes the poison. But in the case of these outcomes, we see effects all the way down to extremely low concentrations. So there's the 12 microgram per cubic meter standard is this sort of red vertical line here. But this is the statistical association from the most recent study that Arden has been involved in, which is as a part of a large aerosol health research center that's being directed by my colleague Alan Robinson at Carnegie Mellon. And here we see on the y-axis now the so-called hazard ratio for cardiopulmonary effects, basically heart attacks. And you see that there's an almost 20% increase in the risk of heart attacks, even at the US standard for air pollution. So these things are causing heart attacks. And we actually understand what's going on there. The particles deposit in the deep lung. That's why the little ones are a big deal, because they have low enough momentum that when you breathe in, they get all the way down in the alveoli of the lung. Of course, now everybody cares about particles and breathing because of COVID as well. But so that the small particles deposit deep in the lung. The local ability of the kind of epithelial tissues in your lungs to deal with that assault of a sort of an antagonist landing in the tissue is overcome. And then the way that the physiology works is that the cytokine levels go up. There's a systemic inflammatory response to that exposure. And systemic inflammation is well understood to increase risks of things like heart attacks. And so that's now at this point quite well understood. And this association is very, very, very robust. So the effects are there. There are strong benefits to improving air quality all the way down to the lowest concentrations that we could imagine. Now, if we look at this globally, and this is more work that's come out of this research center, in this case led by my colleague Josh Apte, who was at the University of Texas, Austin at the time, has moved to Berkeley. But this looks now at the total loss in life expectancy in different countries around the world, and it's just ranked. And we see anything from a half a year to more than a year and a half, 2 years. China and India being some of the more polluted areas, but there's on average around the planet, more than a year of life is lost, mostly through increased risk of heart attack, as I said before. So it's everywhere. It's not just a developed world problem. It's not just a developing world problem. The exposure is general and the outcomes are severe. A more recent example of interest to many people during the lockdown, and this is work from my colleague Albert Presto and his student Rebecca Tanzer during the March, during the onset of the lockdown in Pittsburgh. They have deployed a lot of low-cost air sensors in Pittsburgh. And what you see here are the observations in 2019 in these dashed curves. This is a diurnal cycle, so it's 24 hours averaged over a day. And these are the levels, again, of the fine particle, PM2.5 in micrograms per cubic meter on the Y. And a very classic diurnal cycle here in the pre-lockdown previous season of March 2019, where there are high concentrations at night because the boundary layer is low and emissions are not mixed through very much air. And then as the sun rises, also you have a rush hour right before the sunrise and the boundary layer thickening. Then during the day, the boundary layer rises, so there's more dilution and the levels of air pollution go down. And then that's just lather, rinse, repeat day on and day. And the industrial areas are shown as the black dashed lines, more sensors near major roadways, but away from industrial areas, are the blue dashed. And you see the industrial areas are somewhat more polluted, which isn't a big surprise, but they're high concentrations on each. Now, after the lockdown in Pittsburgh, traffic was just about shut down. It was just, you could almost have a picnic on some of the major roadways and not have any risk. So there was a significant decrease in traffic, and there's no more diurnal cycle of that traffic, and it's way reduced. Whereas the industry around Pittsburgh was deemed essential and did not shut down, and you see that there's still that diurnal cycle. And if anything, it looks like the traffic baseline has just been lowered over the whole region, and that kind of industrial cycle is still visible. So we can see the effects of things like that on air pollution. So now let's turn to those emissions from traffic. And I know that, for example, diesel emissions in London are a big deal. And it's both emissions of organic stuff, the kind of soot, but especially the gases that come out of those cars, because Alan Robinson, who directs that Cases Center, and I have done a lot of work on all of the kind of organic smoke that comes out of most vehicle emissions, other than the crusty black carbon. Everything else evaporates very quickly, and then those vapors do chemistry in the atmosphere, and that some of the products of that chemistry can come back, as you'll see in a little bit. But then also, especially diesels emit lots and lots of nitrogen oxides, and that the NO2 in nitrogen oxides is an equally big deal. And we'll address both of those in the remaining time of this talk. So now let's go to CERN. And I'm lucky enough to be part of this wonderful consortium we call CLOUD, which, as I say, does particle physics at CERN. This is Geneva, the Geneva airport on the right-hand side. And the CERN, the main CERN campus, is this kind of triangular bit in the bottom middle here, and it actually straddles the Swiss-French border. And in the middle of the CERN campus is the 1960s accelerator, which is called the proton synchrotron. But the proton synchrotron is still used as a sort of a warm-up to, it's actually a warm-up to the super proton synchrotron, which is the smaller white circle here. That's drawn, that's not actually on the ground in Switzerland. It's actually many meters underground. And then the super proton synchrotron finally feeds protons into the big ring, which is the Large Hadron Collider, where they do things like look for the Higgs boson. But as part of the proton synchrotron, it's an accelerator, and it can do things other than just accelerate protons. And it can generate beams of what are called pions, which are very good mimics for cosmic radiation, for galactic cosmic rays, which are a main source, because they're extraordinarily high energy, of ions in the atmosphere. And those ions are part of forming clouds. And so we have the capability with that beam of adjusting, sort of turning the flashlight, the torch on and off, or adjusting its levels so that we can control the ion pair formation rate and look at the effect that has on generating particles. So this is the cloud experiment. It's about a 24.5 cubic meter super clean stainless steel vessel whose temperature we can control with incredible precision. It's actually probably the cleanest 24 cubic meters at room pressure on the planet. It's an incredibly clean vessel, and around it we have an array of state-of-the-art mass spectrometers and particle sizing instruments where we can look at the chemistry and physics that are producing these particles with very, very precise control and measurement of all of the conditions that go into this. And it's a large consortium with many of the institutions listed along the bottom. Now at Carnegie Mellon, we deploy an instrument that is what we call a chemical ionization mass spectrometer. We use what's called iodide in this case, I-, to cluster with organic compounds and things like nitric acid that we're interested in measuring, and we can quantify their concentrations. We can also collect particles and warm them back up and measure the temperature it takes to evaporate them off of a filter and determine what their vapor pressure, what their volatility is, and then determine how these organic compounds participate in the formation of particles. So let's look at a couple of the results of some of these experiments before we wrap up this talk. So this is an example of a kind of a typical thing. I mentioned that sulfuric acid, when we looked at those tracks of ship tracks, is part of the deal here. So when you emit sulfur dioxide, it gets oxidized in the atmosphere to make sulfuric acid. And often, if you're around any agricultural activity or any animal activity in general, you will have a fair amount of ammonia in the atmosphere. And ammonia is a base, sulfuric acid is an acid, and acids and bases like to exchange protons and make salts. And in this case, with sulfuric acid and ammonia, you get a salt known as ammonium sulfate. And if you poured sulfuric acid into ammonia, you'd have a very exciting chemistry experiment on your hands. That happens in the atmosphere, not with quite the dramatic release of heat, because they're very tiny concentrations. But what this shows here is that we have time along the x, and we have a particle size measure along the y. And we're looking at the size now. I mentioned 2.5 micrometers. Now we're looking at nanometers, so 1,000 times smaller. And we're looking at 2 to 40 or so nanometers in diameter of these particles over time. And then the color is just abundance. So red is a lot, purple is not very many. This is what we call a nucleation experiment. So we start generating sulfuric acid at time 0, and very rapidly we start to see particles first at 2 nanometers, and we watch them grow up until in a half an hour there may be 10 nanometers in size. So these particles are growing at a rate of perhaps 20 nanometers an hour or so, which is not atypical of what we see in the atmosphere. So in this case, this is what we call nucleation of sulfuric acid and ammonia to make ammonium sulfate. Technically, it starts growing as ammonium bisulfate if you care, but eventually they become ammonium sulfate and they grow up. And we think this is an extremely important part of this process in the atmosphere. In the present day atmosphere, sulfuric acid is almost always involved in new particle formation. And Kamalika has done a lot of work to model a lot of this, along with the rest of Ken Carslow's group at Leeds, to model this chemistry and its effects globally. Now, what my student Ming-Yi did after this was repeat this experiment, but do it now in the presence of nitric acid, which is a much more volatile acid and a weaker acid than sulfuric acid. And this is what happens. The exact same sulfuric acid and ammonia, but now the same thing occurs for the first 15 minutes or so. The particles grow up to about 5 nanometers, and then bang, they start growing much, much more rapidly. And it's a logarithmic scale. And so now, over in an hour, instead of growing up to 20 nanometers or so, they've grown up to 30 or 40 nanometers. So the growth rate is much, much faster than it would have been before. And in fact, under different conditions that are also typical of the atmosphere, I think I'll even show that. Yeah, there's another experiment where they grow even faster. So again, this is the sort of situation. We have sulfuric acid we're generating, so we start generating it here. And then we have a fair amount of ammonia and nitric acid. Again, this is a logarithmic scale. These are in what we call parts per trillion, so very tiny concentrations. There's perhaps 1 or half a part per trillion, that's a part in 10 to the 12 of sulfuric acid. And it's more like a part per billion or 1,000 parts per trillion of ammonia and nitric acid. And those are very typical levels that you might find in a city. And we're looking at conditions that are typical of the wintertime in mega cities. So these are very normal situations here. And so when Ming-Yi did this, again, we see this slow growth as sulfuric acid and ammonia nucleate. And then we get to about 4 nanometers and pow, in very short order, these things are 200 nanometers in size. So they're growing extremely rapidly. And with that, the instrument I mentioned where we can heat these samples up, what Ming-Yi finds is that nitric acid comes off without very much heating, so it's 60 or 70 degrees C, and he has to heat all the way up to about 120 degrees C for sulfuric acid to show up. And that's because the nitric acid is significantly more volatile. There's way more of it. So there's 10,000 counts of nitric acid and maybe 4 counts of sulfuric acid in this instrument. So these particles are almost all ammonium nitrate as opposed to ammonium sulfate. Ammonium nitrate is fertilizer, but it's also a very important, what we call inorganic salt in these systems. So let me show you a couple more slides, and then I think we'll be able to stop and take some questions. So the atmosphere, the urban atmosphere has, this is the kind of NOx side, which I know is a significant concern in the UK and London, anywhere where there's a lot of diesel traffic. But those diesel cars and trucks are also emitting organic vapors. And so we've done experiments where we look at what we call a soup, where we've got that inorganic chemistry going on, but we also have organic compounds that are typical of diesel emissions. And we're using an aromatic compound, naphthalene, which is basically mothballs in this, well, used to be. I hope many people don't use the naphthalene mothballs anymore because it's not very good for you. But this is a succession of experiments that it has recently been submitted for publication by a student from the Paul Scher Institute in Switzerland, Mao Xiao. And what this shows is actually multiple cases, just the same sorts of what we call bananas of particles growing up. But now on the bottom, you see that we observe the composition of these particles. The red is the sulfate part, but these various shades of green are the organic products from this oxidation. You remember, maybe I mentioned that all of the organics that come out of that tailpipe evaporate very quickly, but then they get oxidized. So what we're doing is turning on the lights and oxidizing this naphthalene. We're measuring the volatility of these products using the same instrument where we heat these things up and measure their volatility. And the darker greens are what we see as the total concentration of the stuff that has kind of a low enough volatility it's going to stay in the particles. The circles are the actual volume of the particles that we measure, and they correspond extremely well. So most of the growth of these particles in an urban context is actually the organic stuff that gets oxidized, that's perhaps condensing onto a core that is more of this inorganic salt that was how the particle actually got formed. And we have pretty good mass closure on that. So we understand the chemistry that does that on a mass basis, and we're also, through these experiments at Cloud, getting a better and better handle on what it does on a number basis. So with that, I'd like to wrap up and take any questions that you have. But my thought on this, I'm very interested in this. One of my positions is in a department called Engineering and Public Policy, because the policy connections between air pollution policy and climate policy can sometimes seem either different or even sometimes perhaps in opposition. For example, you might have vehicles that are more fuel efficient, like diesel, but have more pollution emissions, and you could think that there's some conflict between air pollution policy and climate policy. I don't think that's so. The sources of all of these, almost all of this air pollution, is combustion, which is fossil fuel combustion, which is producing carbon dioxide, and we need to decarbonize the energy economy in of order 30 years, really 20, but by 2050. The world economy needs to be heading rapidly toward a fully decarbonized state. So the net emissions of fossil carbon are zero, because the climate effect of emitting carbon dioxide lasts for about 100,000 years, basically forever. Once you do those emissions, unless you actively pull that CO2 back out of the atmosphere, you're stuck with the temperature change that's going to cause. And we have to stop doing that. So we have to stop emitting from combustion, including these vehicular emissions like this. So when we do that, we will cut off most of the sources of fine particle air pollution. Not all of them, but most of them. This is sort of the distribution that we have in Pittsburgh that I've shown here, where the left hand is the mix of organics and inorganics and the sources. So from inorganic fossil fuels, organic fossil fuels, the red and the dark green, and the lighter green would be things like cooking and other activity that is not associated with fossil fuels. And it's maybe a quarter of the total fine particle sources that we know about. And then the right hand pie chart is the different modes of use of energy in general. So heating homes, transportation, electricity, which isn't really a use, but is, that gets distributed to industry and residences and office buildings and such, and more to cars and such. But so when we take the action we need to for climate change, which is more of a global issue, unless you live in the Thames estuary, then we're going to cut the emissions that lead to air pollution by up to 3/4. And that's going to save a lot of lives. Remember, 7 million lives around the world annually. And so they really are very coupled issues. And I think a lot of the path forward, because the benefits of reducing pollution emissions are relatively local, whereas the benefits of carbon emissions and climate mitigation are global, and perhaps slightly more altruistic. Also, the benefits, the fine particles stay in the atmosphere for over a week. As I said, the carbon dioxide stays, or the effect, the climate effect of the CO2 sticks around for 100,000 years. So both the space and the time scales of these things are very, very different, but they both lead to enormous benefits. And so bringing those policy conversations together is something that's of great interest to me. Okay, I think I ran a little bit beyond my allotted time, but I hope we have plenty of time for questions. My look at the clock suggests that we do. So right now, I've either put you to sleep, like my cat Lulu on the left, and if you're just kind of blissed out and resting and listening to, my somewhat soothing voice, that's great. Or else I've caught your attention like Peaches the dog here on the right, which is usually fairly terrifying, but I'll do my best to answer any questions.
Thank you, Neil, for the excellent talk. I lost connection for a few seconds before I invited you. And I was just going to say that Neil is a fantastic speaker, and I think everyone tonight has really enjoyed the talk. There was something for everyone, and I think you've given us some excellent food for thought. I'll start by going through the questions as they came. So let's start with the question from Armin. Health effects are related to PM 2.5 only, so why ultrafine particles are not mentioned in your talk?
So PM 2.5 is all particle mass less than 2.5 micrometers in diameter. So that includes ultrafine. So ultrafine particles, the exact definition is a source of some contention, but is something like particles smaller than 100 nanometers, or even some people say 30 nanometers is kind of the nano cutoff. The particle emissions from vehicles, many of them, there's some soot aggregates that are bigger, but a lot of the particles coming out of vehicles and other combustion sources are 20 or 30 nanometers in size. The nucleated particles I was talking about start at 2 nanometers, as you saw, and grow up. A lot of the climate questions actually have to do with whether those particles grow fast enough that they don't bump into larger particles and reduce the total particle number count, because climate cares about the number of particles. That the epidemiology on fine particle health effects. So ultrafines are part of PM 2.5, but the currently in the United States and in Europe and actually around the world, most of the health standards, certainly the ambient standards, if you go out and measure the particles in air, the health standard is based on the total mass. The dose makes the poison. So there's a very robust epidemiological base for the mass-based standard, the sort of dosage, total dosage. There's a great deal of work, including at our center, into the composition effects. So does those naphthalene oxidation products, are they worse for you than ammonium sulfate? Very likely, yes, and there's a fair bit of toxicological evidence there. Now, ultrafine particles don't have much mass because the volume goes like the diameter cubed, but they are really good at getting into and sticking into the lung. And so the sort of what we would call accumulation mode particles in the trade, I'll try to be a little shorter in my answers. The accumulation mode particles are the ones that are, say, 300 nanometers in size. And we breathe them in quite well, but they're quite sluggish. And so we breathe a lot of them back out. Whereas the ultrafine particles, though they have much less mass, they're small and jittery. It's the same reason they die when they run into particles. But they do deposit better and deeper into the lung. And so it is very likely, and there's a fair bit of evidence, that they have a disproportionate health effect and they're bad per unit mass, but they don't have a lot of mass. And so there's still less really robust evidence on those health effects. And in the United States, we don't have any ultrafine standards.
Thanks.
I swear the rest of my answers will be shorter because I'd like to get more. I have a professorial shortcoming in that regard.
Yeah, let's move on to the next one. Rob asks, given the albedo of the ship tracks, do we need to be using high sulfur fuel to mitigate solar heating?
Yeah, isn't that an interesting question? So we have, in fact, there's an international agreement to do exactly the reverse. And so sulfur has at this point it's been progressively banned near ports. It's been banned in the North Sea for quite a while. It's the same is true around the United States. But my understanding is that this right about now, it's just the low sulfur fuel is now required everywhere. And that does mean, I will try to be shorter, it does mean that we're not so-called seeding clouds as I showed. And you could ask, there's not many people over the open ocean, and is it conceivable that they would be, that it would be a good idea to do that? That's one example of what we call solar radiation management or geoengineering. There are others, like putting particles into the stratosphere. I could spend about the next 3 hours talking about that. So I will just point out that that's where that's a very interesting conversation. If you want to Google David Keith at the Kennedy School for Government at Harvard and get some interesting videos on that, you can do that. And maybe we'll have time for more discussion on that later.
Yeah, I think that's a very good answer, Neil. We'll move on to George, who asks, does more polluted air lead to more cloud formation?
More polluted air does affect clouds. Whether it leads to more cloud formation is actually difficult to answer, but probably no. There is an effect, so the aerosol effects on climate are actually multiple. And the one I described is the easiest one to understand, which is if I have a parcel of air that's rising and going to hit the lifting condensation level, it's going to make a cloud. It hits 100% relative humidity. If I have 5 particles per cubic centimeter, I'm going to get 5 cloud drops. Well, they have to be 100 nanometers or so in size, but I'm going to get 5 cloud droplets. If I have 5,000, I'm going to get 5,000 cloud droplets. I have the same amount of water, I'm going to have much finer droplets. And that's why they scatter more light and they make it whiter. That's called the first indirect effect historically. But also, I've made finer droplets, and that's going to change what we call, the cloud microphysics, and it's going to change the rate of autoconversion, the rate of precipitation formation, and therefore what we call the cloud lifetime. And that in turn might change the cloud extent. If anything, it's likely that the increased number of particles will somewhat increase the cloud lifetime, and that would somewhat increase the extent of clouds. There's not very much evidence that I'm aware of, however, that you go from sort of completely cloud-free to having clouds. So in the atmosphere, when you hit 100% humidity, within about 0.5% of relative humidity, you're going to get yourself a cloud. It's just a question of how many cloud drops you're going to have.
Thanks, Neil. And this is one of the biggest uncertainties, isn't it, in like estimating climate change, the 2 degree versus 1.5 degree uncertainty that we have now. This is a big part of it.
Yes.
Yeah, so Peter asks, slide 21, left plot, non-HNO3 experiments, what processes cause the particle diameter to start to level out between 10 to 20 nanometers? I would imagine that nucleated particles would act as condensation surfaces for subsequent growth to accumulation mode particles. Or am I missing something? This sounds a little bit more technical.
Yeah, I was going to say I've prepared this for a general audience. However, I can answer that question. It's actually the same. Remember, I mentioned for liquid water, I said that the particles need to be 100 nanometers or so in size. You might argue that it's 50 Kamalika. It depends on the updraft velocity and of a lot of other things, as you well know. But in general, particles need to be big enough for condensation of other semi-volatile things to so-called activate those particles. And this is an example of that in the same, it's actually called nanokohler theory in the jargon. And the way that liquid clouds activate on salty particles is called Kohler theory. But what's happening is that the there's a thing called surface tension. You know, it's the meniscus in a glass of water or whatnot. And if you're at 5 nanometers, the amount of energy associated with that surface tension is enormous. And something like ammonium nitrate, which is actually quite semi-volatile, that's one of the reasons it's dangerous as an explosive, is they evaporate. It can't condense on particles that are super small. They actually, you can nucleate ammonium nitrate, but it has to be really cold, and you have to have a lot of nitric acid and ammonia. As we presented that in the same paper here. But in most circumstances, in this case, we're activating 5 nanometer particles. There's just enough ammonium nitrate that effectively the relative humidity of ammonium nitrate hits 100% above for droplets for particles that are bigger than 5 nanometers. But if they're smaller than 5 nanometers, you would need more ammonium nitrate for it to be able to condense. I hope that's halfway clear.
Again, this is like one of the biggest questions of the modeling community is trying to answer.
Yes.
Our next question is, how does the effect of fast growth by nitric acid compare to the one by organics in a typical city environment? Is nitric acid likely always outrunning the organic growth? Interesting.
Yeah, it's a very interesting question. At the end of the day, we can answer that question, and the answer is much of the time the organics win. The reason I can answer the question is once the particles grow above about 30 nanometers, we have lots of ways of measuring their composition. Actually, one particle at a time, we can do it. There's enough mass in each particle, but certainly the aggregate particle mass composition is a function of size. And in many, many, many urban environments around the planet, we and others have done this a lot, the organics are the dominant contributor. But there are places where there's a lot of ammonium nitrate, including around Beijing, which were the conditions that we were looking to simulate here. In Beijing, it actually varies with time. And somewhat geographically as well in the general area of Beijing. So there are places where it happens. It happens much more in winter, again, because the ammonium nitrate is semi-volatile and it likes wintertime. That's also true in the United States, in the Central Valley of California. During the winter, there can be very high ammonium nitrate concentrations in particles because there's a lot of NOx from all the traffic, and there's a lot of ammonia because the Central Valley is agricultural. So it actually depends on location is the simple answer, and time. So winter time, less chemistry, less organics, more, it's cold, so you get a more ammonium nitrate. Thanks,
Neil. The second last question. When you mention combustion, do you also consider fine particle pollution to be from vents from restaurants and fast food at street level? And what's more health impacting, the fine particles or the secondary pollutants that are formed? Focus is often on source control, but should we do more on preventing secondary pollutant formation?
I'll go backwards. Yes, we should. So if we look around the globe spatially, so geographically, the enormous majority of the material on almost all aerosol particles is secondary. I mean, you have to count the sulfuric, the sulfate, the nitrate. The ammonia is primary, but it's a tiny amount of the mass. But the sulfate and the nitrate are produced by chemistry in the atmosphere. And actually, most of the organic stuff is also produced by chemistry. As I said, especially from vehicles, it all evaporates, it gets in the gas phase, it does chemistry, it returns to the particles. That's a major chunk of research that my own research group has done over the past 20 years. You are right that cooking particles are less, cooking particles are stuff like oleic acid, which is, actually a methyl oleate. They're not very volatile. And there seems to be less of that cycle of evaporation and recondensation of an oxidation product. We don't know whether the oxidized products are more toxic or not. That's an extremely insightful question. My suspicion is yes, that we tend to wind up with nitro-organics and nitro-polycyclic aromatic hydrocarbons and things, and those are known to be very, very toxic. Their specific toxicity is very high. On the other hand, these things are more water soluble, so you could imagine they would sort of clear from the epithelium better. than a more sort of oily particle might. And so you could make counter arguments. But yes, indeed, there are, I haven't mentioned that sort of quarter of the pie chart that are from things like cooking. There was an experiment in London a few years back called ClearFlow, where these so-called cooking organic aerosol were very evident, and actually in many of the measurements, Beijing as well, New York City, we can look at diurnal patterns of different types of organics, and there's one type that has this little peak around 12 noon, and it's the cooking organic aerosol. So those are there. They do. You know, we in my own group, a student of mine did a single particle measurement paper where, when we're very close to restaurants or very close to roadways, we can see those individual particles from cooking and traffic. I don't know whether one or the other is more toxic, and there's no standards, and at this point we're just getting to the point where we can make the atmospheric observations. The epidemiologists can do nothing without the observations to do the associative statistics. And so at this point, we don't have a sufficiently large set of observational data for the epi folk to even have a chance. That's not the only way to investigate the toxicity, but it's often where we start. So I don't know.
Thanks, Neil. If I may add, again, there's this uncertainty about how the secondary particles are formed, where projects like experiments like the Cloud CERN experiment come in and they tell you how they are formed, so you can prevent it.
Yes, indeed. And we also have experiments that Jasper Kirkby would never let us do this at Cloud, but we take diesel cars and we take the emissions from the car, we dilute them down so that the smoke evaporates from the primary particles, and then we oxidize them in a thing we call a smog chamber, and we look at the change of composition over time from that. And as I said, we've done a great deal of work on that at CMU.
Sure. So the last question is, what proportion of fine particle pollution is caused by non-combustion, such as from brake and tire wear?
Two parts of an answer to that. One is not very high. So tire wear, brakes and things, those are they're in all of the inventories. They tend to be larger. So you tend to find more of that mass in the supermicron mode and above 2.5. So in what we call PM10, the 10 micron mode tends to have somewhat more of that, which is also where more of things like dust and pollen live. And your nose is designed it's evolved to be very good at filtering out that stuff, which isn't good for you during allergy season, but it's a preferable outcome. And so most of those particles deposit in the upper respiratory tract. Now there are tire wear and such particles that are smaller as well that you can ingest and inhale into your deep lung. What has, however, become a bigger deal recently are what we call volatile chemical products. And what's going on here is that in many parts of the world, the kind of traditional sources of pollution, the cars, even though I keep pointing to cars in this conversation, are so much cleaner than they were 40, 50 years ago. It almost isn't funny. I mean, they are 1,000 times, literally 1,000 times cleaner than they used to be. And so we have made great strides, especially with spark engines, but also with diesels as well, in reducing the pollution emissions. They are still there, and they're still very important sources of air pollution, but we've gone a long way to reducing that. Also industrial emissions, many other sort of usual suspect sources of pollution. And that means we're starting to see more of other sources of pollution that are things like paint solvents, personal care products. You'd be surprised how much secondary organic aerosol comes from body wash, siloxanes that are in skin creams and deodorants. We see them, my colleagues see them in the atmosphere. And those also do the same cycle where those vapors oxidize and condense. Sometimes it's the very same molecules. So perfumes use terpenoids, things like alpha pinene and other terpenes, which are the things that come out of trees that we've spent a great deal of time actually looking at Cloud and in other places. But sometimes they're quite exotic engineered compounds like siloxanes that you'll never find coming out of any tree ever. And those are starting to be a larger and larger fraction of the total fine aerosol concentration.
Right, thank you, Neil, for the fantastic talk. As I said, there was something for everyone, and I think that was also evident from the questions that we had tonight. It was very enjoyable for me as well, personally. Can I ask everybody to thank Neil on the chat box, because that's all we have. We can't have a full clapping for you, but I'll do that because it was such a good talk. And yeah, that's all for tonight. I thank Neil again for agreeing.
Well, I thank you, and for your, sorry to talk over you, Kamalika, but I really want to thank you, and the audience was wonderful. Those were type A questions. They were really excellent.
Yeah, it was quite a diverse set of questions that we had. And thank you for answering them so well and so much in detail. I just want to note to the viewers that we do have another talk coming up in February on the 23rd, where PhD research will be showcased, PhD research going on in the University of Leeds. Thereafter, we have another talk coming up on the Arctic, which will be, again, a really interesting project like Cloud, cutting-edge science, and I'm sure you'll enjoy it a lot. And with that, I'll take your leave. And thank you again, Neil, and we hope to see you again at the next talk. Good night. Take care.